Just give me 1 second. Oh, it's going to take time. I have another way also, but let's see this one. Or I can, I have another arrangement. I'll better put with that. Change my camera. I hope you can see my screen, which is here, and I'll make it spotlight for everyone. So can you see my screen, everyone?
Yes, sir.
Yes, sir.
Fine. So let's say our first question is about the deep learning models, right? Now here, generally, what a model is trying to do, we have to look into that. So if we want to say reliability about, like, in a way, this question was answered by next question by Sumit, that to take the multiple criteria, right? So now deep learning model, many times we have to look into what is the purpose of them. If deep learning model we are using for class, general or common use is classification. That means we have certain input parameters, right? Set of input parameters based on which we will classify this into multiple possibilities. Maybe let's say in relativity, let's say fail, pass, or say, let us say this is faulty, this is not faulty, right? Or many other criteria. You may have multiple categories also. So here generally the deep learning models reliability will be meaning that the classification error is less. That means we generally are concerned with the how much is the classification error in the deep learning model. That means how correctly it is able to give you the right output. So here the error becomes kind of measure of unreliability, right? So what is the probability of error, right? That means how many times it made an error, right? Divided by total number of experiments which you have done or total number of data points you have selected, right? Many times we are interested in particular error. That means false positive, false negative, or true, right? So there also we may be interested in how many times it is correctly classifying and how many times it is wrongly classifying. That means it is saying certain category, but it is opposite. So this confusion matrix or this probability of error is many times can be used as a similar representation of the relativity, but this is only giving you the performance, relativity performance of the model. It is not giving you the performance of the data or performance of this outcome. How well is model is able to classify? We can get it by the error probability. So that's why whenever you are writing such papers, you generally use various error measures like mean square error, average error, right? And various other metrics, R square, etc., which is focused on telling that this error is minimized. If less error means that you have your classification is done very correctly. Okay. Mr. Chhatrapal, do you have any other query, or do you think that this was your query?
I have, sir, one more query also. Like as today we are working on deep learning projects as well as some machine learning projects. So, what do you think about reliability in these projects? Same concept will be applied there also?
Yeah, see, whenever we are saying now, then first you have to talk about which reliability we are talking about, right? Reliability of what, right? So deep learning, or it's a mostly a classification problem, right? Or machine learning, it's mostly a classification. It is like our human mind. Whenever we certain situation, we judge it into certain, that what does it mean into a certain outcome. So judgment is based on the observations which we are making, right? So how correctly we are able to judge a certain aspect, that is giving us the reliability, right? So, or we can say unreliability is the possibility of error. Okay.
Okay, sir. Okay.
So if you're saying project, then actually there are many. If you're looking at the project aspect, then project will be successful or not, that is again a question. So you have to see that project success, how do you define, right? How do you define that project will be successful? Then based on that, you can find out what is the chances that project will be successful and what will be the chances that project will not be successful. So there are different concerns, and because of that, we have to use different probability measures to define the performance, reliability, performance, or risk evaluation, right? Okay. Is it okay?
Yes, sir. You
Okay.
are saying right. Risk analysis is also important factor which cannot be neglected.
Yes. So
We
for
have to
risk, then
think.
you have to use multiple criteria, right? So like making a false positive error may have different risk. Making a false negative error can have a different risk. So you may be controlling the error probabilities in to the different values for different kind of errors. Okay.
Yes, sir. That's why in all projects we have to do the calculation or probability of risk analysis. Also, that is also a very important factor, I think.
Yes. So this is also same thing. Okay. Thank you. Mr. Sumit, can you elaborate a little bit more about your query, Mr. Sumit Tomar?
Sir, I wanted to know, let's say I have certain objective to achieve, and
Okay.
other than that main objective, I have certain other aspects. Let's say it is with respect to the safety, sir. That
Mhm.
safety has also to be maintained.
Yes.
So my final objective, which is there, I suppose it will be impacted by when I will be considering the safety aspect. What I understand is, sir, my final reliability will change. And can I say in this case that I have two objectives? Like one is my final aim should be achieved in a company with that safety measure should be safety should be
Yes.
maintained.
True. So there are various ways of considering this, right? That we can say that there's some function which we have to do, but there are multiple parameters. Let us say we are concerned about performance parameter 1, performance parameter 2, 3, like that, right? So here there may be different performance levels associated with them. So here, if we are considering reliability, before evaluating the reliability or before evaluating the success probability, we have to find out that combinations of these performance values, in what combinations they will be considered as success, in what combination they will be considered as failure. Like for each performance parameter, if we have certain range, a certain value, a certain threshold, right? So if all has to meet, that means it's a kind of series system where all performance parameter has to be met. That means you will multiply you will consider the probability that all performance parameter has to be met. That means any failure in any performance parameter is not acceptable. In that case, reliability will be multiplication of the probabilities that what is the probability that it will be meeting each and every performance criteria, right? So uh, multiple criteria, whenever it is there, you can take their values, you can make their combinations, and you can say that which combinations are success combinations and which combinations are failure combination. Many times, like I discussed with Mr. Chatrapal also, same is applicable in your case also, that rather than reliability, we are more interested in risk here, right? So when violating one performance, it is having one kind of consequence. When violating another performance, it is having another kind of consequence. So we may have a different reliability requirement for different performance requirements, right? So for each one, we have to evaluate separately the failure probability and the consequences. So risk is a better approach to address such situations, that we are able to evaluate how much is the total risk for a certain kind of scenario, right? So in a risk, we are taking various consequences, consequence 1, consequence 2, consequence 3, and assigning with their probabilities. So we get a complete spectrum. Rather than taking single value, we are taking multiple set of values where different consequences are given associated with different probabilities. And that helps us to understand what to do, whether it is acceptable or not acceptable. Is this the same thing, Mr.
Yes, sir. Rightly said, the risk is the right word actually, which should be used. Actually,
Yes.
to be very specific, sir, I wanted to share a case like, for example, if I have a weapon which I need to activate on my enemy side, and parallelly I have a requirement that it should not activate while I am carrying it with my own carrier. So that is
Yes.
also one of the major requirements. So
Yes.
as you rightly said, I
And
suppose the risk is the right word rather than calculating the
true.
probability part.
So if we are calculating reliability, then both has to work. That means the probability that it is not fired when we are carrying, and it is fired when we are using, right? So both probabilities should be multiplied to get the system reliability, right? But what happens? Why we need to go for the risk? Because uh, when we are carrying and it gets fired, that is having the higher consequences. So we generally desire high reliability or lesser failure probability of this is inadvertent operation, right? Inadvertent operation or the wrong firing is more dangerous. So we want to ensure that there is a less probability of that. When we are firing, if it doesn't fire, we have little comparatively lesser consequences. So that we may demand with a lesser reliability, or we may be able to tolerate a little high failure probability, right? So generally the different consequences are there. So we may be assigning different probabilities and different risk for that. Right? So very rightly you said, and very rightly you have pointed out that that risk can be a better way of treating this problem. But again, to evaluate risk also, we have to understand the reliability, right?
Thank you, sir.
Thank you. Uh, Rajvardhan, Jigyasu. Mr. Jigyasu, do you have any query?
No, sir.
Okay.
I'm audible, sir.
Yes, yes, pretty much.
Yes, no, sir, no, sir.
Okay. Thank you. So let's continue with discussions we were having. Yeah. If anyone has any other query, you may put it up. I'll be happy to discuss. Okay. Fine. Let me do one more thing. Okay. Fine. So we will discuss about this system. So now we will try to understand the probability distribution. So in probability distributions, we use T-term, PDF and CDF. So when we are talking about the discrete random variable, right? So discrete random variable means the random variable which have the discrete values, the quantities, right? It's not continuous. In that case, for each possible outcome, we will assign a probability. So here fx is the probability, and sum of fx here, if we do, the probability will be 1. And each fx has to be greater than equal to 0. In the case of discrete, small fx will be also less than equal to 1, right? And probability of x equal to x is equal to fx, right? And CDF, whenever we say, we have to see that CDF is having less than equal to sign. So probability that x CDF fx f1, if I want to take, that will be probability that random variable is less than equal to 1. That means it will be counting the value of 1 as well as value of 0, or if negative values are there, minus infinity to x ft, right? But if we use continuous random variable, right, in that case we do not use here the term which we use is the probability distribution function, because here it is telling how probability is distributed among the values of outcomes. But here and here the measure of fx is also the probability only. It is a dimensionless quantity. But when we say probability density function, this is applicable for continuous random variable, and fx here is not a probability, it is the probability density. That means integration of fx over a range or over complete range gives me the probability. Area under the curve gives me the probability, but this value which I am taking is the density. So that means it is telling me where the probability density is high or low. But if I want to know the probability, I have to area under the curve, right? So if I want to know the probability of x to b, a to b, then I'll integrate from a to b. Now here in continuous random variable, even if I put equal sign or if I do not put equal sign, it makes no difference here. Can anyone tell why? If I say probability that a is less than equal to x is less than b is equal to probability that a is equal to probability that both all are same and that all are equal to a to b fx dx, right? Can anyone tell why this is true? So for continuous random variable, what happens? That point is a dimensionless quantity. So probability of a is 0. Probability that x is equal to a will be equal to 0. Probability that x equal to b will be equal to 0. Because here a and b are the point values. And for continuous random variable, that point is not defined. That point is dimensionless, right? So because of that, these probabilities turned out to be point probabilities are 0. There is no area under the curve, so there is no probability. It will be 0. So that's why for continuous random variable, we are not much concerned with the equal or less than equal to sign. But whenever we talk about, so this I can also calculate as f of b minus f of a, right? But I cannot do the same for the this discrete random variable. There I have to be cautious. If I write f of 2 minus f of 1. So this means probability f of 2 means probability of 1, probability of 2 and probability of 0, right? And minus f of 1 means probability of 0 and 1, right? So that will be reduced. Only probability of f of 2 is remaining. Okay. A1 is not counted. But same thing if I say probability of x less than equal to 1 to 2 for continuous random variable, this will be same 1 to 2, right? So if I want to calculate probability of 1 and 2 both together, I have to make it probability of f of 0, right? Then only I'll get the probability of 1 and 2. Because of this equal sign, it has an impact here, but this equal sign will not have any impact in the continuous random variable, right? Just for information. What is CDF? CDF is the integration for the continuous random variable from minus infinity to t. And ft will tend to 1 as t will be tending to infinity. Okay. So integration of fx dx over the full range. So area under the curve for fx is always equal to 1. Similarly, for discrete random variable, if we sum up the probabilities, generally we represent like dot and this. Okay. And this is fx, this is x. So if we sum up all probabilities, my sum of probabilities will be equal to 1, right? Then comes the terms mean and variance. In engineering, we generally make decisions based on two things only, mean and variance. In regular life, we only consider mean, right? But in engineering or when we are making critical decisions, we also have to consider the variance, right? So variability in the value is clouding our decision making. because sometimes the value comes 1, sometimes the value comes 5. Now, which one is correct? I don't know, right? So if whenever I'm doing something which is having multiple possible outcomes, and anyone can happen at any moment randomly, so still I need to make a decision. So to make a decision, I generally use mean and variance, right? Or mean and standard deviation. Right? If I know the two, it gives me an idea that where how my values will be varying, and so where is the values are centered and where the values are, how much is the variation there. If more variation there, that means values spread is over a larger range, and it is difficult to decision making, because to get a sufficient number of observations within the range, we are calling that as a confidence interval, right? Let's say if I want 90% confidence interval, that means 90% of the values I'm expecting to fall under this range. So this range will be wide. If the range is wide, it will not help us to make a decision. It will cloud our decision, right? So to make a proper decision, rather than using central value, we are using a range. So if let's say if I'm talking about risk, so I know that from my estimation, risk is going to fall somewhere in one, let's say 1 fatality per 100 year, right? To 2 fatality per 100 year, right? So now I know, and based on this range, I can make a decision, right? But if I did not know that range, let's say mean is somewhere 1.5, but let us say if variability was high, then this would have been, the range would have been 10 per year uh, to 10, sorry, this can be 0.1 to 0 per 100 year to, let us say, 10 per 100 year. Now the decision making would have been difficult, because here the range or the variability is high. So when variability is high, but still, if my criteria is acceptable here, my risk is acceptable, 10 per year is acceptable, then I will go for it, fine. Even though variability is high, I'm able to make a decision because I know that the risk is still outside my acceptance range. Yeah. Same way, any value when we are using, because there is a variability in the values, like life we discussed, right? So life is coming for any system. Let's say we go for purchasing a fridge, or we go purchasing a bike, anything. What will happen? The different persons will experience different life, right? So it's not going to same. But if we say on an average, the life is coming to be 10 years, and 90% of the users have experienced life between 9 to 11 years, right? Then I'm pretty confident that, okay, that I'm not, because most of the time it is going to be 9 to 11 years. Like same way, if I say 99% is falling somewhere 8 to 12 years, right? Then also I may be satisfied. But in other cases, that 99% of the time, the value is coming between 1 to 15 years, right? Or 1 to say 19 years with mean 10 years. Now here in this case, that mean 10 years is not going to help us. So variability should also be known. If variability is known, we know that where the chances are more, where where most likely our experience will be also be coming into the picture. Where is most likely our what kind of experience we will be having with the product, right? So variance along with mean gives us an idea that what kind of values we are going to, what are the chances we are going to experience with that product, right? And once we know that, this helps us to make a decision. So mean, as we calculate, mean is the kind of weighted sum, that whatever is the value multiplied with the probability of that value. When we do, we get the mean for discrete random variable, and sigma square is the difference of the value from the mean, and the square of that multiplied by the fx, the probability of that event. Similarly, for continuous random variable, we take the integration x fx dx, right? Because fx dx gives you the probability in that region. And here we use x minus mu whole square into fx dx. Okay. covariance, we use the term for the two random variables to know whether they are dependent or not. So covariance is expected value of intersection of the two minus their mean. So covariance is also telling us whether they are negatively correlated, positively correlated, or highly correlated, or zero, there is independent. If they're independent, this value tend to be zero. Expected value of xy will be mu x into mu y. If they're dependent, positively dependent, that means value of x will be higher when value of y is higher, then this value tends to be higher. So this value will be some positive value. If they're negatively correlated, that means if value of x is lesser, then value of y will be higher. In that case, they will be negatively correlated and this value will be smaller than mu x mu y, and that will be negative value. So covariance can be used for that purpose. Now let us discuss some random variables. First, we will discuss discrete random variable. Discrete random variable in reliability we are using for the group of the items. Right? So when we have a group of the items, how do we get the random variable, which is the number of failures or number of success? So whenever we are discussing discrete random variable, our concerned variable x is generally representing the number of failures. Right? How many failures we are going to observe? So let us see that first random variable, first distribution is the uniform distribution. Uniform distribution is generally for k number of values. So we have 1, 2, let's say k possible outcomes. For each possible outcome, whatever is the probability fx, that is going to be same, right? Since all are same and we know summation of fx is equal to 1 and all are same, so that means let us say that is equal to p. So summation of p I equal to 1 to k will be equal to 1. So k into p will be equal to 1. So p will be equal to 1 upon k, right? So we get the probability of each event as 1 upon k. The mean of this is 1 upon k. Fx is, we know fx is 1 upon k and multiply by value. Value is x. So x by k, when we sum up, we will get the mu. Okay. Similarly, sigma square is fx will be out, x minus mu whole square. If you add up, that will give the sigma square. Okay. There is another distribution that is called Bernoulli distribution. Like this is coin. So whenever we toss a coin, there is only two possible outcomes, head or tail. So any event, any trial is called a Bernoulli trial if there are only two possible outcomes. So generally it is very widely used in quality, reliability, and many cases, because most of the time we are dividing the values in two possible outcomes, head or tail, 1 or 0, or saying success or failure. So generally the two categories, whenever we are saying one category has to be marked 0, one category has to be marked 1. So let us say if we can reversely mark also, we can call success as 1, failure as 0. Whatever you want, that way you can calculate. But let us say if I say that success is 0 and failure is 1, then the value P will be the probability of 1. That is probability of failure. If I say success is 1, failure is 0, then P will represent the probability of success. Okay. Many times, because I'm interested in number of failures, so that's why generally I will represent failure as 1. So what is the probability of failure? That is P. What is the probability of success? That is Q. Q is equal to 1 minus P. So this I can represent by this P to the power x, Q to the power 1 minus x. So when I put x equal to 0, this will become P to the power 0, Q to the power 1, that is equal to Q. That means probability of success is Q. When I put x equal to 1, that means P to the power 1, Q to the power 0, that is equal to P. So probability of 1 or the probability of failure is P. What is the mean of this? Mean of this is P, and what is the sigma square? Sigma square value is given as PQ. Binomial distribution is a where we have the multiple systems or multiple events which are coming into the picture. So here we have the n number of items which are independent to each other, but they are also same. So they're identical and independent. n items which are identical and independently distributed. Okay. So let's say for each item, the probability P is given and probability Q we can get by the 1 minus P. So let's say P is the probability of failure, right? So Q will be probability of success. Now let us say I have n items. Let's say in my room I'm having, let us say, 4 bulbs. Okay. Now I'm sitting here. If one of the bulb doesn't work, I'm fine with it, right? But if 2 doesn't work, then also I may be fine. But if 3 doesn't work, I am remaining with 1 bulb, and that 1 bulb I do not find sufficient enough, even in degraded cases, to do my job. So in out when there is 4 bulbs, or let us say 2 bulbs are necessary. If less than 2 bulbs are there, then I will not be able to work. So that means in this case, I'm coming across a special system, that is K out of M, right? That means 2 out of 4 should be in good condition for my system to work, right? So how can I calculate this probability? Now each system is, let us say, failure probability is P, right? Or if I say, and let's say reliability is Q, but generally we use whenever we are considering good system, P will be the reliability and Q will be the failure probability. What does it mean? 1 represent the success and 0 represent the failure in this case. Okay. So, or we can take opposite also. P is unreliability and Q is reliability. Right? So many times we are interested, let us say P is failure probability and Q is success probability. Now I want to know what is the probability that 2 out of 4 system. That means minimum 2 systems are required to work for the system to work. So 2 bulbs are required. So in that case, 2 bulbs working and 2 bulbs failed is a success. 3 bulbs working, 1 failed is a success. 4 bulbs working, 0 failure is a success. 1 working, 3 failed is a failed state. 0 working, 4 failed is a failed state. Right? Now I want to know these reliabilities. So my failure probability is, let us say, 0.1, and let's say my success probability Q is equal to 0.9. Right? Now I want to know that what will be this probability. So I can calculate this probability. How will I calculate? What is the probability that 1 working, 3 failed? If I want to know this, what is the X? X is the number of failures here, right? Because P I am taking as the failure probability. So X will represent the number of failures. So X is 3. 3 out of 4. N is 4 and P is how much? 0.1. This will give me the probability that 3 are failed out of 4 units. How can I get this? In each case, what is happening? Let's say I'm having 1, 2, 3, 4, bulb number 1, 2, 3, 4. So I will be having, in what cases 3 can work and 1 can work and 3 will fail, like this, right? Failure, work, failure, failure, right? Failure, failure, work, failure, 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 work. How many such combinations are possible? That is 4C3, right? Out of 4, 3 are failed. How many such combinations are there? 4C3. So that is NCX. Out of N, X is failed. So in each case, how much is the probability? The probability is 1 working. So that means Q raised to the power 1, and 3 are failed. That means 3 P to the power 3. Right? This I have to sum up 4C3 times. So this will be multiplied with 4C3. So this is our binomial distribution. Binomial distribution is giving me that what is the probability of X number of outcomes or X number of failures out of N devices given probability of failure is P. Or I can use the same formula for calculating number of success, that probability that X number of success is there out of N items, given that P is the probability of success. Is it okay? Is it understandable? So how will I calculate reliability here? Reliability here will be in two cases. That is binary 3, 4, 0.1 plus binomial of 4 failure out of 4, 0.1. These both are the failure cases. So if I subtract from 1, I will get the reliability. Or I can also get it reliability as success probabilities. That means binomial 0 failure out of 4 with 0.1 probability plus binomial 1 failure out of 4, 0.1 probability plus binomial 2 failures out of 4 with 0.1 probability. In 3 cases, I will have the success probability. If I sum, this will give me probability. I sum it up, I'll get the reliability. Or I calculate the failure probabilities and subtract from 1, that will give me the reliability. So for K out of M, good system or bad system, we can calculate reliability or unreliability using this binomial distribution. This binomial distribution, okay, first thing, if you have any query, are you able to follow or is it not understandable? Anyone? Could you understand what we mean by K out of M system? K out of M, like let's say I'm having 4 generator, like bulb example I have taken. So even one bulb is not working, I'm still able to work. 2 bulbs are not working, I'm able to work. Same way we may have generators, motors. So we may have some more motors than we require. So if some is not working, we will be able to still able to do the job. Any queries? Am I audible?
Yes, sir.
So do you have any query, anyone?
Yes, sir.
Yes, please. Is it understandable? So binomial distribution can also be used for solving this K out of M problem, right? Or binomial is also used for general case. Like let's say I'm having I'm using 4 bulbs, right, in my office. Now I want to know that the failure probability of 4 bulbs in, let us say, 1 year is 0.1. That means in 1 year, the failure probability is 0.1. Now I want to know that what is the mean. Mean means what? Expected number of failures, right? Because random variable here is the failure. X what represent is the number of failures. Okay, this is number of failures. N is what? Items, total items. And P is what? Probability of failure, right? If I want to know that if I'm using 4 bulbs, how many is the expected number of failure in 1 year? So first I will get the probability of failure in 1 year, that is, let us say 10%. So how much will be the expected number of failure? That is 4 into 0.1. That means 0.4. If I'm using 10 bulbs, this will come out to be approximately 1 bulb, right? So in a way, this value gives me an estimation that how much is the average number of failures or expected number of failures which I'm going to observe in a certain period. Okay. So this is used widely as mean value function or expected number of failure in repairable systems and other systems. Then sigma square is the NPQ. How much is the variability in my estimate? That is given as NPQ. N multiplied by P multiplied by Q. So standard deviation will be the square root of this. Many times, like let's say if N is coming somewhere around 100, right? So for 100, let us say I'm interested in calculating the failure probability of 10 out of 100, right? So let's say X is 10 and N is 100. Now what will happen? I have to calculate NCR. So NCR will be factorial 100 divided by factorial 10, factorial 90, right? So calculation of such quantities by even computer can be difficult. Computer cannot give you the factorial value of 100. It is too large for computer to calculate, right? So it may give you problems. So when values of N are large, then this formula becomes difficult to calculate. So this binomial distribution has two kind of approximation. When value of P is somewhere around middle 0.5 around, then binomial distribution can be approximated into normal. So for normal, what will happen? We will use mu equal to NP and sigma equal to square root of NP Q. And same normal distribution we can use for getting certain number of failures, probability values. Let's say we take an example that X is a random variable representing number of failed components among 5 independent identical. So N is equal to 5. Out of which component has one chance of 100 in failing. So P is equal to 1 in 100. Okay. So X can have values 0 to 5 and it's binomial distribution. Find the mean number of failures. So mean number of failures will be NP. So that will be 5 by 100. And that will be 0.02. Okay. Variance will be NPQ. So that will be 5 by 100 into 95 by 100. Okay. Sorry, P is 100. So P is 1 by 100. So Q will be 1 minus 1 by 100. So that will be 99 by 100. Okay. This we can multiply and get it. So mean number of failures, variance we can get, and probability of exactly one failure. Exactly one failure means one failure, so 1 by 100 raised to the power 1, and rest of the 4 working. So failure probability is 99 by, success probability 99 by 100 raised to the power 4. And how many such combinations are possible? 5C1. So that will be 5 into 1 by 100 into 99 by 100 raised to the power 4. Right? When we calculate this, we will get the probability of exactly one failure. Right? Is it okay, everyone? You can raise your query if you have some query related with this or near around it, because this is more basic mathematics. Poisson distributions, when we use, then we use this formula. The difference in Poisson and binomial is given a number of items, how many items are failing. Here we use lambda t. We use the time that for a given time. This is very much used in the repairable system analysis. Right? So for repairable system, let us say we have 10 years of life, right? In 10 years, multiple times it can fail. So how many times on an average it will fail? We will say failure rate is lambda, and or we can say T divided by MTTF or MTBF. So on an average, it takes time to failure is MTTF. So how many failures we are expecting is T upon MTTF. So mu will become this 1 upon MTTF. If we write as lambda, so this will become mu equal to lambda T. Average failure rate multiplied by T. Similarly, we can say mu for repair. If we are considering, then this may be the repair rate multiplied by the time. This will give the expected number of repairs which we will able to do. So mu gives this, and once we know the mu, we know the probability e to the power minus mu. If I write lambda, then it's e to the power minus lambda t raised to the power x divided by factorial x. This is my Poisson distribution. Poisson distribution has same mean and same variance. So Poisson binomial distribution can be approximated as Poisson when n is large. If p is one of the quantity, p or q is very, very small. Okay. So in that case, what will happen? NPQ, because one is very small, one is very large. So the large quantity will be near to 1. So this will become NP and both will become NP. Right? So Q we will take, which is the large quantity, and P we will take the smaller quantity. And Same formula we can use for calculating the probability. Let's take one example. Let's X be discrete random variable, and which is representing number of failures and subsequent repairs of restorable system over a 1 year period. Okay. So let's say it's Poisson distribution with mean failure rate. So lambda is equal to 2 per year, 2 failure per year, right? And our time is how much? 1 year. Failure in 1 year. And we want to know the probability of X equal to 1. Probability of X equal to 1 will be the probability that e to the power minus lambda into t into lambda into t, that is 2 into 1 raised to the power x, x is 1 divided by factorial x. When we use this formula, f1, that not more than 1, right? Not more than 1 means 1 or 0. So that is probability of x equal to 1 or probability of x equal to 0. For probability of x equal to 0, this will become again e to the power minus 2 into 1 multiplied by 2 into 1 raised to the power 0 divided by factorial 0. Okay. Once we sum it up for the two values, we will get the probability value. So 40.6 is the probability, 40.6% chances there that you will see 0 or 1 failure, right? Anyone having any query with these distributions? Anything you can ask, any queries about it or something related with this? Anyone? So generally
Clear, sir.
these, yes, please. Huh? Is it okay? Understandable?
Yes, sir.
Okay, thank you. So let us now, but what happens generally in reliability, we are dealing more with the continuous distributions because we are interested in probability of failure or probability of success. What is the probability of RT? We are interested in RT or we are interested in FT, right? That means we are interested in time to failure distribution. What is the probability of success or failure? So generally what we do for continuous random variable, we can know what is the individual failure probability, right? And if I want to study number of failures, I will use these discrete random variables, where P I will calculate by using these continuous random variables. In continuous random variables also we have uniform distribution. So uniform distribution like this from A to B, it is going to have the same probability. So that means area under the curve has to be same. So 1 upon b minus a will give the fx. Right? Here I used to take one example that here fx need not to be a value between which is not necessarily has to be 0 to 1, right? Fx is any value greater than 0 for continuous random variables. Like if I say my a is equal to 0.1 and b is equal to 0.2, right? If I say this, then what will be my fx? Can anyone tell? So A is 0.1 mm and B is 0.
10.
So Fx will be 10 per mm, right? Here Fx is, if you see, this is not a probability. This is the probability density. So this has a dimension also per mm. See? Mean value of this distribution is given. So what will be the mean value? Mean value will be 0.15, right? And how much is the variability? That is B minus A whole square divided by 12. So that means 0.1 whole square divided by 12. That is 0.01 divided by 12. Okay. Then next important distribution is the normal distribution. Normal distribution is also called Gaussian distribution or bell-shaped distribution. Many names are there. It is called normal distribution because in general, we expect that most of the things are distributed normally. That means we generally look like this. Wherever is our target value or wherever the process is targeted, wherever is the target, we will have the maximum occurrence there. And then it will decrease on the both side. Occurrence probability density will decrease on both sides. So this is given like mu is the central value and this is a symmetric. It has only two things, that is mu and sigma. Mu is called mean, sigma is called standard deviation. But what happens? We cannot get capital Fx for this, right? Because this is not integrable. So that's where is the problem. So but this has an advantage. How mu and sigma affects? Let's say if I change the sigma, but mu is same, then what will happen? Sigma 2 is greater than sigma 1. What does it mean? Standard deviation for 2 is more than 1. What does it mean? More variability is there. So the same area will be covered in larger range. So spread will be higher. Since spread is higher, value will be distributed more. So peak will also come down. When we take another example where variance is same, but mean is different. In that case, what will happen? Mu2 is greater than mu1. So what will happen? Distribution will be centered in other place, but it will look like same. Here, if we see the case where mu1 is less than mu2 and sigma 2 is larger than sigma 1, right? So larger variability is actually having more uncertainty, because in a larger range, the value will be spread and which will confuse us. But normal distribution, though it is not integrable, we are still able to solve because of one property, that we are able to transform this normal distribution into a standard normal distribution by taking x minus mu upon sigma as the z. Right? This value x minus mu upon sigma, we can take it at z. So with that, with the transformation, whenever we use this, fx will turn out to be 1 upon under root 2 pi e to the power minus half z square, right? So actually differentiation of this will give 1 upon x upon sigma is this. So 1 upon sigma will be divided by this. So that will give this. Sigma will disappear. So there is no sigma, no mu. So fx, if you see here, fz has become single value distribution. So for given value of z, I will have the single value of fz. There is no parameter which is changing the distribution. So it's a standard distribution. Cumulative distribution, I can get it by taking the integration of this. So numerical methods are used. So for standard value, because this is single value, there's no variability is there. So we can get the distribution. Okay. So PDF looks like this and CDF looks like this. If you see, this is curved in between. Wherever this 45 degrees there, you will call that as an inflection point, which is somewhere around the mean, right? 0.5, right? So 0.5 will be at the 0 if it is the standard normal distribution. Or otherwise, it will be different. Let's take one example that wear out of an old drilling bit is normally distributed with mean of mu is 120 hours. And standard deviation sigma is 14 hours. Drilling occurs 12 hours each day. So each day we are doing 12 hours operation. How many days drilling should continue before operation is stopped in order to replace the drill bit? 95% reliability is desired. That means whenever system is reaching 95% reliability, I will stop it. So my target reliability, we know phi is fx, right? Or ft. So reliability will be equal to 1 minus ft. So that will be equal to 1 minus capital phi of z. Okay. And what is z? Z is x minus mu or t minus mu divided by sigma. Okay. Now this reliability which we want is 0.95. So 0.95 is 1 minus phi x minus mu divided by sigma. So phi mu x minus mu divided by sigma will be equal to 0.05. Okay. So from normal tables, we get the z value. Z value is coming out to be, which is giving 0.05. The value pi inverse of 0.05 is coming out to be minus 1.645. Okay, but I'm interested in x. So what will be the x? X minus mu divided by sigma is minus 1.645. So x will be equal to minus 1.645 into sigma plus mu. Mu is known to us 120, sigma is 14. So 120 minus 14 into 1.645. And this gives me T equal to approximately 96.97 hours. So 96.97 hours and 1 day is 12 hours. Approximately 8 days you will be able to have. That means that to make sure that our reliability for the bit is not falling below 0.95, I have to replace the bit every 8 days. So in a way, I'm doing kind of PM here, preventive maintenance here, right? That I'm not letting the reliability to or the conditional reliability to be falling beyond 0.05. Conditional reliability falling above 0.05 or going above 0.05. That means 95% of the time it is 95% chances there that it will not fail. Okay, if I replace the bit 95% or higher, I replace the bit every 8 days. Any queries, anyone? But normal distribution is not used so widely in the reliability to capture the reliability patterns, because we are mostly seeing this kind of patterns where the model case is not there, which probability of failure is either increasing or decreasing over the period of the time, failure rate. So most of the time we whenever we use, most of the time we find that log normal distribution is fitting to the data, and log normal distribution is giving at like this. So if X is following log normal distribution, what does it mean? Ln of X will follow the normal distribution. So if some data is following the log normal distribution, if you take log of the data, it will follow the normal distribution, and rest is same. So Z will become here ln of X minus ln of mu divided by S. Okay. So once you use this, so ln of mu is actually called ln of T median, because when T is equal to T median, Z will be equal to 0. That means, and when Z is equal to the 0, phi Z is equal to 0.5. So phi of 0 is equal to 0.5. Median means 0.5 value, probability is 0.5. So we can use this. So Z will become this, and same what we do for normal distribution, we will do it here to get the probabilities. Let's take for one example that if we have the T median as 5,000, right, and S equal to 0.2, then we want to know MTTF, variance, mode, and everything. If you see, the formulas are given. MTTF is T median e to the power S square by 2. Mode is T median divided by e to the power S square, right? And median is already given, so we can calculate. And variance formula is also here. Sigma square, that is T median square e to the power S square multiplied by e to the power S square minus 1. So we can use these formulas to calculate MTTF, sigma square, sigma, T mode, right? And reliability. Reliability means 1 minus 5, and I want to calculate for 3000. So ln of 3000 divided by 5000. 5000 is the T median, and S is ln of T minus ln of T median. This is also equal to ln of T divided by T median, right? Both are same. So either I take ln of 3000 minus ln of 5000, or simply I take ln of 3000 divided by 5000, both will be same. And this gives me the reliability. So I can calculate reliabilities for log normal distribution. So if I intend to achieve what is the life for 0.95 reliability, that means this value I have to equate to 0.95, and I have to reverse calculate. Reverse calculate formula is same. I will calculate the Z. From Z, this will be equal to Z. And when I solve this, I will get the value of T, which comes out to be 3602. Okay. In reliability, more popular distribution is the exponential. If you see that reliability, any user who is not doing any detailed study, you ask what is reliability, he will say reliability is e to the power minus lambda t. This is the popularity of the exponential distribution. That every design, wherever you find, because we are more concerned about the useful life period. The infant mortality period is removed, and we do not want our product to reach to the wear out period. So most of the time we are operating the product in the constant failure rate region. This constant failure rate region is represented by the exponential distribution, and this constant value of failure rate is called the lambda. It is not a function of t, it is not changing with time t. So we know RT is equal to integration of lambda dt e to the power minus, and if we say, because lambda is not changing, so it will become e to the power minus lambda t. Right? So this becomes the simplest distribution. If I want to take fx is minus dRT over dt. Okay. So differentiation of this will give minus lambda e to the power minus lambda t. Okay. And minus is already here, so minus will become plus. Anyone was asking something? Mean is 1 upon lambda, variance is 1 upon lambda square. So if you see, in this case, mean is 1 upon lambda and standard deviation is also 1 upon lambda. So if you see that variability in this case is very, very high. The variance is very, very high. Whatever is the mean, same is the variance. So coefficient of variance, if you take COV, it is 1. Mu upon sigma is equal to 1, which is quite high. So sigma upon mu is 1. Exponential distribution has a memoryless property. That means it does not remember its age, right? So the probability of failure, let us say I have let's say failure rate e to the lambda is equal to 0.1 failure per year, right? Now let us say I'm talking about a system which has crossed, which I have used for 5 years, right? And I want to know that for 5 years it has worked. I want to know the reliability for 6th year. That means I want to know reliability for 6 years given 5 years has been passed. So how will I calculate e to the power minus lambda into 6 divided by e to the power minus lambda into 5. This we already know that t plus t0 divided by t0. Okay. This formula we already know. Anyone has difficulty with this formula? How do we get it? So this will become e to the power minus 6 lambda plus 5 lambda. That is e to the power minus lambda. Right? That means for 1 year reliability, let us say I want to calculate reliability of 7th year. That means 7 given 6. Again, that will be e to the power minus 7 lambda divided by e to the power minus 6 lambda. Again, it will turn out to be e to the power minus lambda. What does it mean? That whether the equipment has spent 5 years, whether the equipment has worked for 6 years, it doesn't make any difference in the failure probability for next 1 year of operation. So this system does not remember that it is aging. It is having a memoryless property, right? It is not affected by the age. So here the item failure rate is same as it was when the item was new. So item is not aging. There is no impact of age. Age neither is having improvement in reliability nor having deterioration in reliability. The reliability for 1 year or half year or 10 year is remaining same irrespective of the amount of years it has passed working. Okay. So that is the memoryless property. Generally, electronic and electrical component have their failure times obeying this distribution because generally they are not stressed much, and because of that, most of the time they do not reach to the wear out region. So most of the time they will working in this constant failure rate region. And because of this assumption or because of this generally observed failure pattern, we are able to simplify many things because we know MTBF is 1 upon lambda or MTTF is 1 upon lambda. Many calculations we are able to do, which is very simpler in nature. Another thing, when let us say e to the power minus lambda t, right? Let us say when and lambda is 1 upon MTTF. So I can also write it as e to the power minus t upon MTTF, right? So when t is equal to MTTF, this reliability will become e to the power minus 1, and e to the power minus 1 means around 0.8 and 6, 3. Right? That means 36.8%. So what does it mean? That when T is equal to MTTF, I'm expecting 63.2% failures, right? And only 36.8 will be surviving. Any query? So if you are working, so here like we many times get confused because for normal distribution, at 50% we were having 50% failure were when T was equal to mu, mean. But here when mean is T is equal to mu, 63% failure are there. Only 36% or 37% is only working. Okay. Median value we can calculate using this formula. Okay. Let's take one example that a transmitter is having constant failure rate this. We want to calculate MTTF, median life, reliability, and design life. So MTTF is 1 upon failure rate, right? MTTF is equal to 1 upon lambda. So 1 upon 0.00034. Median life, we already see the formula here, 0.69315. So multiply by 0.69315 if I do, then it will give me the median, T median, right? And if I want to know calculate reliability for 30 days, that is e to the power minus lambda t. So lambda is 0.00034 into t is 30 days, because this is operating hour. Since this is operating hour, we have to convert days into hours. So I have to multiply by 24. Okay. If I want to know the design life for 0.95, so I'll take 0.95 here, e to the power minus 0.0034 into t. I want to know this t. So I'll take ln. Ln is 0.95 will be equal to minus 0.00034 into t. So t will be equal to minus 1 upon 0.00034 ln of 0.95. Okay. So I can calculate all these calculations are given here, and I can calculate this. So design life comes out to be 150.86 hours. The last distribution for today's discussion is Weibull distribution. Weibull distribution is so popular that whenever we are doing failure data analysis, we call it now as a Weibull analysis, right? It is so popular. That means most of the failure data we are able to fit into the Weibull distribution. Weibull distribution has two parameters, beta and theta, and this is given as reliability is given as e to the power minus t upon theta raised to the power beta, right? Here theta is called scale parameter, beta is called shape parameter. If you change the theta, what will happen? Only the scale will change, right? Because let's say if theta is doubled, then if you double the values of t, you will get the same reliability. If you make theta half, then you change the values of t by half, then you will get the same reliability. So that means by increasing the theta, you are increasing the spread, right? And if you're decreasing the theta, you are decreasing the spread. Okay. In lesser, same look, but that scale will be changed. It will be contracted or expanded, right? While beta is changing the shape. When beta is less than 1, it will look like this. When beta is greater than 3, it will take a kind of model shape here, right? Almost looking like a normal. When beta is some other value, because what is happening, t to the power 2, t to the power 1, power is changing. Whenever power changes, the shape changes. The failure rate for this is given as beta upon theta, t upon theta raised to the power beta minus 1. So if you see, if I put beta equal to 1, what will happen? This will become t to the power 0. So only thing which will be remaining is beta upon theta. So lambda t has become independent of t if beta is equal to 1. So when beta is equal to 1, this is same as exponential distribution where lambda is equal to beta upon theta, right? When beta is less than 1, what will happen? It will be 0 to 1. So when beta is less than 1, then this will be negative quantity. It will be less than 1. So let's say beta is 0.5. 0.5 minus 1 means 0.5 minus. So this will become t to the power minus 1 by 2. That means as t will increase, the lambda will decrease. So this is called decreasing failure rate. When beta is greater than 1, then whatever happens, let us say I'll take beta is equal to 2. So be 2 minus 1. So this will become proportional to t. If I take 3, this will become proportional to t square. That means as t rises, the failure rate rises. So that is called increasing failure rate. So we have three conditions. When beta is equal to 1, it is constant failure rate. When beta is less than 1, this is decreasing failure rate. When beta is greater than 1, then I have the increasing failure rate. Mean of this is given by here. This is called gamma function. Gamma function values are available in Excel and available in some tables also, from there you can get this value. And this is the form which is solved to get this, but we do not need to solve this. We can get the gamma values directly from the tables or the software, whichever we are using. And sigma square value is given by this formula. We can calculate this and use them. Okay. Whenever here, if you see, if t is equal to theta, then what will occur? It will become minus 1 raised to the power beta. So whatever is the value of beta, when t is equal to theta, then you will have reliability as e to the power minus 1 of failure rate, failure probability as same 1 minus e to the power minus 1. As we discussed earlier, same like exponential, right? When t is equal to theta, then we will have 63.2% failure, right? Same here. Okay. So that's why theta is also called as characteristic life. Theta, eta, many names can be used. Okay. This we have already discussed. Many times we have 3-parameter distribution for Weibull. So this is called location parameter. Like if you change gamma value, this is the starting point. Up to that gamma, this will be having no failure. If I increase gamma, nu will be looking like same, will have same values, but it will shift towards right. So gamma represent generally the time which is the free from failure. That means there is no chance of failure when t is up to gamma. Failure will only possible after the gamma. If such cases happen, then only we can use this. Sometimes rather than using gamma, we use t0. We write e to the power minus t minus t0. Sorry, e to the power minus t minus t0 divided by theta whole raised to the power beta. Okay. How does it look? Let us say when we use, as I discussed, when beta is less than 1, it will always look like an exponential distribution, right? When beta is little larger than 1, then it will be increasing. So 1.5 is this one, right? It is skewed. And when beta is around 2, it will start taking the shape, but it's still skewed. But when beta becomes higher than 3, it is almost looking like a normal distribution. Failure rate, how does it look like when beta is 0.5? Then decreasing failure rate. This is one, decreasing failure rate. Beta 1.5, increasing failure rate like this. Okay. And when beta is 2, linearly increase. Right? When beta is 4, this is parabolic, or fastly increasing failure rate. A compressor wears out with a linear hazard function. Lambda t is given to us 2 into t divided by 1000 into 1000. Okay. 2 into 10 to the power minus 6 by t. So can we estimate MTTF, variance, design life, etc. So we compare that beta upon theta, p upon theta raised to the power beta. So t raised to the power 1. So that means beta is equal to 2, right? So if I put it here, this will become 2 divided by 1000 multiplied by t divided by 1000 raised to the power 2 minus 1, which is same here. So from this, by comparison, I can get beta is equal to 2 and theta equal to 1000. Okay. So we can calculate our MTTF is theta, gamma function of 1 plus 1 by beta. So 1 plus 1 by 2, and this comes out to be rate 86. And I want to know the design life for 0.99. Variance is theta square, gamma of 1 plus 1 by 2, 1 by 1 minus 2 beta, 2 upon beta minus gamma of 1 plus 1 upon beta whole square. When we use this, we will be getting this. Similarly, reliability I want to calculate for. So my target reliability is 0.99. So that means this value is equal to 0.99. I reversely calculate. How do I do this? I take ln of 0.99. This will be equal to minus t upon 1000 whole raised to the power 2, right? So I can take t upon 1000 will be equal to minus ln of 0.99 square root, and t will be equal to 1000 square root of minus ln of 0.99. This will come out to be 100.25 hours. So I can calculate why I am calling this as a design life, because my design intent will generally not be to fail all. I want to know, I want to promise a certain level of reliability for the product till for the product life. So if my target is, let's say for product, I'm specifying 0.99 reliability. So my design life will come according to the life at which I'm observing 0.99. If I say 0.95 accordingly to that, this will become my design life. So depending on the reliability requirement, my design life will change for the same system. So these are the references which I've used. So I'll stop here. This has been little bit little high. Today we have discussed the mathematics behind the reliability evaluations, right? So here our major distributions are there. If we know the distribution, can we calculate the reliability? So if we have the data, we are not discussing that part. If we have the failure data, how do we calculate find out the distribution? That is a very simple. You take the data, you fit it in, you use any like a NIT, MATLAB, any statistical tool you use, you can fit the data and find out the distribution parameters. Once you know the distribution parameters and distribution, you can calculate the reliability. Okay? Or you want to calculate maintainability, you take the time to repair data, fit it into the distribution, and you will be able to calculate the maintainability. For reliability, you take TTF data, time to failure data, you fit it into the distribution, you will get the reliability values or the unreliability values. You can get the parameters of interest, whatever you want, by taking the data, fitting into the distribution and getting the values. So I think this was all which we wanted to discuss here today. This was mostly basic probability, right? And using the probability for reliability evaluations. So I would request you to provide your queries, etc., whatever you have. I think I have exceeded the time by large. Okay, so still, please have your queries. Or anything, if you want to have a discussion, anything, right? I think everyone should be tired, right? It's long.
Yeah.
Long, that is also very late hours. Okay.
Please raise the query if anyone have anything related to today's talk or yesterday's talk. Anything if in your mind.
Yeah. I think
Okay.
everyone is tired now.
Yeah.
We have gone with a pace. It will take certain time to revise it, and then maybe.
Sure, sure. Anytime you can connect with me. Right? I think my contact details will be shared, or if it is not already shared, I'll share it here. So you can always connect with me. Okay. I'm also offering one NPTEL course. This time I have new course I'm offering, Introduction to Reliability. If you're interested, this is just going to start. So you can, if you want, you can join, see that. There it is more relaxed and you will be having sufficient time to go through it. Same thing what I'm discussing here, similar things will be available there.
That's good. So I think we can conclude if there is no query are there. So Professor Goyal has written his email ID in the chat box along with his mobile number.
Mobile number is also there, so you can connect me anytime, right? No issue. This NPTEL course, I can also share that link. If you want, you can go through that because NPTEL is almost freely available. In this course, most of the things are there, basic things. Fine, so let us call it a day. Yeah.
Okay. Thank you, Professor Goyal.
So everyone, can you please turn on your videos?
Yeah, Vijay, I forget it. Please.
Everyone is almost sleepy.
Yeah.
Thank you, sir.
Thank
so
you.
much.
Thank you, everyone. Good night.
Yeah.
Good night, sir.
So tomorrow,
you,
tomorrow we will have the next topic is the system reliability modeling, and which will be delivered by the Dr. Ajit Kumar. He is the industry consultant and presently working at Bangalore. So we will be assembled here at 7 p.m. Thank you very much. Thank you all. Yeah, thank you.
Thank you, sir. Good night, sir.
Thank you, sir.